All right, so going from a sentence to a word equation, level of confidence. 5. That's easy. Yeah, 5, like I can do this in my sleep. 0, I don't know who you are. Okay, lots of 4s, lots of 5s. I think that's fairly... 14? Really? No. I think that's fairly straightforward. That's pretty easy. A few of the fine points on that. So, like in the first one, we're told that magnesium metal burns in air to create magnesium oxide. So we don't write magnesium metal. We don't write the word gas in a word equation. We just write the name of the chemical or the compound. So magnesium. And when we're told this is a metal, this is a gas, this is a solution, we just put in the state information like that. And I mentioned to you that whenever it says burns, that means it's reacting with oxygen. So, and that's always reacting with oxygen gas. So if it, sometimes it'll say burns in air. You know, it's not reacting with the nitrogen component of the air. It's not reacting with the carbon dioxide in the air. It's reacting with the oxygen in the air. So that makes sense? Okay. And you all understand the distinction between sentence and word equation, right? That's one that historically I always think seems so easy, so I kind of gloss over it. And I stressed it a little bit more in that tutorial because typically in this chapter we get to the test and somebody writes sentences for their word equation. I'm like, no, you just rewrote the sentence I gave you. So I wanted to make sure that that was clear. Magnesium, okay, magnesium oxide. And you weren't given state information for the magnesium oxide, so you can't put it in there. There will be situations where you don't have state information, and that's fine. A few tricks that I do want to share with you about sort of, we could call it inferring state information. So you know, anytime it says, you know, magnesium metal, copper metal, zinc metal, that's a solid. If it says hydrogen gas, oxygen gas, nitrogen gas, obviously you get that that's a gas. When it says hydrochloric acid, you're actually being given the state information, you just don't know it yet. So all of those acids that we talked about, whether it's hydrochloric, whether it is nitric acid, sulfuric acid, what are some of the other acids that you were given? I guess those are the only ones. Acids are always in aqueous solution. So you know that to get the formulas for the acids, you just have to look those up. And eventually you'll look them up enough, you'll just have them memorized. Some of you may already know HCl, that's a pretty common one. So that's actually just hydrogen chloride. It's a molecular compound. It's only really hydrochloric acid when it's in an aqueous solution. Left to its own devices, that would be a gas, and it would be a gas cloud you would very much not want to walk through because you don't want to breathe in hydrochloric acid. You know, nitric acid, same thing. So nitric acid, and of course, you know, you have to just look up the formula HNO3, but that's just hydrogen nitrate. It's nitric acid because it is hydrogen nitrate in aqueous solution. And we'll talk a whole lot more about that when we get into the chapter on acids, chapter 15. But just so you know, when you see hydrochloric acid, sulfuric acid, nitric acid, those are always in an aqueous solution. So what you have is a bunch of water with hydrogen chloride dissolved in it or hydrogen nitrate dissolved in it. Okay? Yeah. So you had a few where it mentioned water as a product. And whenever we say water, that's liquid. So it's not an aqueous solution. Water is the solvent in an aqueous solution. But water is liquid H2O. And typically, so one of two things would be true. We'll either say and produces steam or produces, so you know, If it just says water, you can assume it's liquid. Sometimes it will say produces water vapor. Then what are you dealing with? Gas. The other one that you'll sometimes see is gaseous water is the way that it gets referred to. And very occasionally, I would say that the least common way to refer to water vapor is as steam. But of course, if you see the word steam, you know that that is gaseous water. It's water vapor. We don't deal with solid water typically in chemical reactions. Most of them happen above that temperature. Things are moving slowly enough below zero that you don't get a whole lot of reactions. You get some. But in general, the faster particles are moving, in other words, the hotter the materials are, the faster reactions happen. We actually don't really talk about rate of reaction much in here. We'll talk about it a little bit later. Other questions on anything on the front?
So when we're writing out an acid?
So in the word equation, where you're just putting the state information, you would put hydrochloric acid aqueous. So, yeah, you always specify that's an aqueous solution. Other questions on the front? On word equations and formula equations? Okay. Let's work on balancing number 7 together and see if the person who wrote the sheet screwed up or not. Okay, so here we have the word equation and the formula equation. If you're having a hard time balancing, are all your formulas correct? Okay, let's work on balancing. Okay, so on this one, notice that I am splitting the hydroxide ion because it doesn't reform as a hydroxide ion on the other side. So the sulfate ion I can balance as one thing. The hydrogen and oxygen, and of course I have to look at oxygen that is not existing in the sulfate ion. So I've got here 2 hydrogens, 2 plus 4, I have 6 hydrogens, and I have 4 oxygens, 1 sulfate ion, 1 lead atom, and here I have 2 hydrogen, 1 oxygen, 2 sulfate, and 1 lead. Are those the same initial tallies that you have? Were you counting the oxygen in the sulfur, in the sulfate? No? Were those the same initial tallies you had?
No, I put the oxygen together.
Oh, the hydroxide ion? Okay. Yeah, and you can't do it that way because it doesn't appear as a hydroxide ion on the product side. So let's go ahead and balance this real quickly. If I wanted to balance the water right off, I could put a 3, well, save that one, Moser, save that one. Okay, so if I want to balance the sulfate ion, if I put a 2 there, that now gives me 12 hydrogen. I should do these in another color, huh? So if I put a 2 there, that gives me 12 hydrogen, 2 sulfate ions. Sulfate is now balanced. Lead is balanced. Maybe I won't have to do anything with lead. If I wanted to balance water, I would put a 6 here. That gives me 12, and nope, that gives me 6, so that doesn't work. So you're kind of looking at common multiples. This one may be real boogery, I don't know. Let's see, common multiples. It really helps if I don't screw up the math to start with, doesn't it? Okay. Yeah, that would be not 12. I have 4 plus 4. That's 8, which means I shouldn't put a 6 here. I should, in fact, put a 4 here, which gives us 8. And it gives us 4 oxygens, and what do you know? Everything's balanced. Whoops. Thanks. I was going to work myself into a veritable frenzy over that. Yes, ma'am. The question was, do I have to rewrite my balanced formula or my balanced chemical equation? No, you really don't. What you do have to do is show 3 lines. So you have to show a word equation, a formula equation, and then another line where you're balancing it. Okay? So you do have to leave one unbalanced as the formula equation. That's something that people trip up on a lot, and they just balance on that, and I almost did it myself. But you do have to recopy that so that you leave a formula equation, or you're not showing the formula equation. You're just showing word equation, balanced equations. Other questions on this? Do you want to take, did you get stuck on 7 and stop, or did you do 8 and 9? Yeah, we can do 9, absolutely. Okay, so we've got our word equation, formula equation, and somehow I missed a letter in there. And now we're going to go ahead and balance it. We cannot leave, of course, the ions in ammonium nitrate intact because they're all breaking apart. So what we have is nitrogen, hydrogen, and oxygen. Nitrogen, hydrogen, and oxygen. We obviously can't get any new stuff. So here we have 2 nitrogens, 4 hydrogens, 3 oxygens. Here we have 2 nitrogens, 2 hydrogens, 2 oxygens. And I'll switch color for clarity. So, you know, we don't have anything that's left all by itself, which are the things that are easiest to balance. But, and we also know that anything that we do in terms of coefficients on the reactant side changes everything. Because you only have one reactant, which is a real pain in the tuchus. So, if we attempt, well, we know that for oxygen, we're going to have to come to 6, basically. There's sort of a subtle art to looking for least common denominators and common multiples, or what would be lowest common product.
I only have to go to 3.
Really?
I only have to go to 2.
Oh, I see. Hold on. If we do this, what do we get? Oh, then we do get 3, and then we get 4, and then we're done. Well, never mind. So much for all my theorizing. I blame the sinuses. Well, you know what, and this is a good place to model all the mistakes you can make. One of the mistakes you make, I call the upward death spiral. So instead of a downward death spiral, it's where the numbers just keep getting bigger and bigger and bigger and bigger. And generally, when you get trapped in one of those, you're going to get to a point where it all balances, but then you look at it and you go, oh my God, I can reduce that by a factor of like 10. So it happens. I've done it myself. If you start getting into that, just get it to balance and then look at it and reduce it, because you can simplify. You know, if everything there divides by 4, okay, I went a little bit too far. I got carried away. So it happens. Question. So how do you get 3 out of this? Well, what you have to remember is that you've got 2 oxygens here and 1 oxygen here. And these are the toughest ones. So you're just getting your total number of actual oxygen atoms. The toughest ones are where you've got an element that's in multiple compounds. So you change one thing, and it's not as easy as going, oh, okay, 2 times 1, that's 2. Oh, wait, I still have to deal with this guy over here. So that's, yeah, those are the ones that are most prone, I think, to screwing up. Okay. Who had already gotten this? Okay, good. Let's do number 9. Okay, so we've got calcium oxide added to water gives you calcium hydroxide. And if we do our initial tally, we have 1, 2, and 2, 1, oh. Guess what? It's balanced. Okay. Sometimes you get lucky like that. There are a couple that I can think of. And yes, those very often leave people scratching their heads because they're like, no, but I need to. No, actually you don't. It's fine. So let's talk a little bit about some of the other symbols that go into equations. I wanted to kind of wait until we were all together to do this. So level of comfort, what I'll do is tomorrow we'll have a FIP quiz on going from a sentence all the way to a balanced formula equation showing all the steps. Good? So let's wrap up a few odds and ends, and then I'll cut you loose. I'll put the homework assignment up and you can get started on that. Okay, so if you look in your book on page 246, there is this lovely little chart that is titled Symbols that are used in chemical equations. And some of these you've already been using. So, yields is that single arrow. It means the reaction proceeds in one direction. It doesn't go backwards. What you should also recognize, however, is that you will sometimes see an arrow that looks like this. What that means is that the reaction is reversible. So the reaction can run with A plus B as the reactants forming AB, but then AB can also decompose back into A and B spontaneously. And there are some reactions that do this until they find a point of equilibrium. So those are reversible reactions. Let me cut that and move all this up because it looks like people are straining to see it.
So would you have to say that twice?
What?
Double reversible? Or just don't do it?
What do you mean?
Do you have to show it on both sides?
Yeah, when you have that reversible reaction arrow, you don't need to recopy it in the other order because what you're saying with that reversible reaction double arrow is, hey, this runs both ways. So, and we don't deal with, honestly, we don't deal with a whole lot of reactions that do that at this level. As you go further in chemistry, you will. Okay, the representations of state, I think you've all got. Solid, liquid, gas, and of course that odd one that's probably new to you, the aqueous solution, something dissolved in water. You have all consumed aqueous solutions, I am sure. Aqueous solutions of sucrose are quite popular. Aqueous solution of sucrose is sugar water. Add some citric acid. Aqueous solution of citric acid and sucrose I rather enjoy on a hot summer day. Lemonade. Yep. So you can go home and impress your family and friends with, I'm going to whip up an aqueous solution of citric acid and sucrose. Anybody want some? And if you have a geeky family, they'll love it. And if you don't, they'll just scratch their heads and go, oh, that one. Okay. So there's something, we talked a little bit about precipitate in the video where I said, you add two things and suddenly the solution goes cloudy, you've formed a precipitate. It's when something that was a new substance is created and it's not soluble. Sometimes a precipitate is really dramatic and it doesn't just go cloudy, like actual chunks start to appear suddenly. And we often say that the precipitate has come out of solution. Okay, the solid has come out of solution. And the symbol that's sometimes used to indicate that is that we have, let's see, AB plus C yields AC, which precipitates, plus B. And so that downward arrow indicates that, let me get rid of some of the stuff here at the top. Let me shrink it. That downward arrow, and we really honestly hardly ever use that at this level of chemistry, but you may see it on stuff. I don't ask you to use it typically. So what we're saying, and typically that would be that AB were aqueous, C might have been an aqueous solution or a liquid. Actually, yeah, that's a more likely scenario. And what we get out of that is AC as a precipitate plus B in some form. I don't know what form, but we're telling you there that AC is a solid, but that it has precipitated out. Like I said, we don't use that one a whole lot in this level of chemistry. Similarly, if we have something that's given off as a gas, so if we have zinc plus hydrochloric acid, and that forms zinc chloride in aqueous solution, but it also forms hydrogen gas. We sometimes use that up arrow to indicate that something's gone sort of up an energy state. So this is now a gas, an insoluble gas that'll bubble off. So that's shown for gases if that gas is coming, it's moving up an energy state. Again, we don't use it very often, just like the solid down arrow for precipitates, but it can be used, so I want you to be aware of it. Not one that I expect you to know. Not one that we use a whole lot. The one that I do expect you to pay some attention to is when you see something like this, or this, or this. So that delta, are you familiar with delta from math? It means change in. In chemistry, in the chemistry context, it actually refers to heat, to heating a substance, which I hate because in physics it's all delta, delta, delta change. So I tend to actually do this. There are some reactions where you have to heat the reactants in order to get them, you have to give them a burst of energy in order to get the reaction to run. So that little delta sign over the yields arrow means that you've heated the reactants. Because of switching brains between chemistry and physics every day, I tend to prefer this, though I expect you to know either of them. This electricity would mean that you're decomposing something. Typically it's decomposition. You're adding electricity to get a reaction to proceed. And there was one on your practice sheet that said water decomposes with electricity. And so there, as an example, and that process is called electrolysis. We'll talk a little bit more about that when we talk about types of reactions. But you would have liquid H2O. Okay, can't write. Gives us gaseous hydrogen and gaseous oxygen. And I expect you to recognize that when you see it. The other ones, the last four on that chart, you have specific measures of pressure, so 8 atmospheres, that this reaction has to be carried out at a certain pressure. This is more an issue for reactions that involve gases, but honestly, we don't really see this until we get into chapter 11, where we're talking about reactions with gases and the ideal gas law. So we don't much deal with that. They show also sometimes just the word pressure, indicating that you have to be above normal pressure. So you have to have it in a pressure vessel of some sort. I don't really care about those much. We don't use them. The one that I do want you to be aware of is this. When you see something like that, that's telling you the temperature at which the reaction is being carried out. I'm going to shrink all of this. So if you are running a reaction at 100 degrees, and remember this is always, always, always in Celsius, and you see H2O as a reactant, what state is it in? So let me make that even better. 101. It's a gas. You know, so if you're given this piece of information, I expect you to infer that piece of information. Likewise, X plus whatever, if you're told that X plus H2O and the reaction is run at 25 Celsius, what state is the H2O in? Liquid, Celsius. 100 to 0 is the liquid range for water. 25 is room temperature. It's probably 25 in here right now. Actually, it might be like 22. But, yeah, so we don't see a whole lot of reactions that are run at super low temperatures that involve water, because water doesn't react very well when it's in a solid state. So I do expect you to know that. And the last one is catalysts. We will not really use catalyst information at all, because we don't talk about catalysts until much later in the year, if we get to it at all. Questions, comments, concerns? Okay. Basically, if you want to run down, if you want to put a little pencil dot in, oh, you don't have your books, huh? I'll tell you what, I'll put a picture of this up. So in your book, I've got marks by the ones I expect you to know. Yields, reversible, state symbols, so solid, liquid, aqueous, gaseous, and especially the heating, and it's hard to see, but the one where a specific temperature is shown for a reaction, I expect you to recognize that. Okay, let me get the homework assignment out. Okay, there's the assignment. This is, of course, the Chapter 8 review, and it begins on page 269, and I'll stick it on the board, but you can get started on that. What I will say is these are the ones that most pertain to the quiz you're going to have tomorrow, because those are the ones where you're actually going from a sentence to a word equation to a formula equation to a balanced chemical equation. So you might want to start with those. I know it makes some of you crazy to start out of order, but if you can bring yourself to do it. Okay, that's it.